Today we discuss magnetic monopoles. But before I come to magnetic monopoles, I received a video yesterday, and I thought I'd show that. This is sort of the state of the art. This is the same kind of string loop that we saw earlier, except that this is now in full field theory and in general relativity. So now people are evolving field theory plus general relativity on the computer, and so the evolution looks something like this. So at the bottom you see these gravitational waves coming out, and whenever there are episodes of kink collisions, then there's a burst of radiation, of gravitational radiation as well. So anyway, this is, I just received it last night, so I thought I'd show it. All right. So again, so for magnetic monopoles, there are again some excellent references, and there's the book Solitons and Particles. There's an article by Sidney Coleman, Magnetic Monopole 50 Years Later. Again, the article by John Preskill. And these are two books on magnetic monopoles. So let's first think about a simpler situation where we just have scalar fields and no gauge fields, then and consider a triplet. So phi is actually 3 components, and the Lagrangian is simply the gradient squared and then the potential. And so the vector phi has to have magnitude eta. So that's the constraint coming from the potential. So then you can imagine a situation where the length, which is mod phi, is fixed to be eta, but the direction of phi changes in this hedgehog kind of way, pointing out everywhere. In this case, the value of phi at the center is kind of is not determined, because you can't have the Higgs pointing in every direction at one point. So it ends. So you have to have the magnitude be 0 over there, and so you're going off the vacuum manifold. So phi squared cannot be eta squared everywhere if the direction takes this orientation. So in this case, you can write the equations of motion, and you can write phi hat to be eta times some function of the radial coordinate, and then pointing out in the radial direction over here. And there are boundary conditions you have to impose, that f0 is 0, because you know somewhere that the wave has to vanish, and that at infinity it is 1, and then you find some solution. So if you wish to do the exercise, this is a simple exercise. You can find the exact profile. There's no analytic solution, but there are good approximations that can be made. Okay, so let's come to topology now. So what happened here was that we had this triplet. The vacuum manifold is phi squared equal to eta squared. So phi 1 squared plus phi 2 squared plus phi 3 squared has to be eta squared. And so that's a 2-sphere. So the vacuum manifold is a 2-sphere, namely given by phi equal to eta. And space at infinity in 3 dimensions is also a 2-sphere, right? So you have, so basically phi at r equal to infinity is a mapping from S2 of space to S2 of the vacuum manifold, so which is kind of illustrated over here. So in principle, what you can have is that this, you can have a complete wrapping of the vacuum manifold. So for example, if you took phi at infinity to be just eta and everywhere pointing in the third direction, then this would have winding 0. But you could choose phi at infinity to be pointing in the radial direction. So that means the north pole goes to the north pole, and all points go to the corresponding points. Then this is like an orange peel which is wrapped around the orange, and there's no way to eat your orange unless you puncture the peel. So that's the topology, that there's a winding number. And in terms of homotopy groups, this is the statement that pi 2 of S2 is the set of integers. So you can have winding of 1 or 2 or 3 or -1, -2, it can be anything. So some integer. The other thing to note is that in terms of symmetry, this Lagrangian has an O3 global symmetry, which means that you can do a rotation of phi, the vector phi, and you will get the same thing. So that's the symmetry. So one cautionary remark I want to make is that if you have non-trivial topology, it implies that there are certain singularities. By here, singularities means points where the order parameter cannot be in the vacuum manifold. So just by choosing the directions in a certain way, you are forced into having points which do not lie in the vacuum manifold. And if they don't lie in the vacuum manifold, then there's non-vanishing energy over there. However, non-trivial topology does not imply a static solution of the equations of motion. That you have to check separately and by solving the equation of motion. And even if a static solution exists, topology does not guarantee its stability. So you have to keep that in mind, that the only thing that topology is implying is that you can't be on the vacuum manifold everywhere. Okay, so now let's include gauge fields. So now you have the covariant derivative of phi squared, where the covariant derivative is defined in this way. It's a little confusing sometimes because these fields, this W carries two indices, the mu, which is the space-time index, and then the vector sign is actually the internal index. So this cross product is an internal space, right? Because it's like the third component of this would be the first component of W times the second component of phi, and so on. And the gauge field strength over here is defined in this way. It has a quadratic piece, as you can see. So it's a little more complicated. And then the potential is the same. This again has O3 gauge symmetry, but this time it's a local symmetry. However, in the discussion of topology, only the vacuum manifold was involved, and the gauge fields played no role. Okay, so this is the discussion of topology doesn't really care about whether it's gauged or global. There is one exception, which are called semi-local defects. I'm not going to go into that here, but there are exceptions, and that's because you'll be minimizing the energy, and we've only been focusing on fields that minimize the potential energy, which means that you are considering fields which are independent of space and then defining your vacuum manifold. But if you start considering fields that are not uniform in space, then you have to worry about the gauge terms as well. Anyway, we can come to that later if you wish. So if the topology is the same, then even the gauge model should have gauged monopole configurations and maybe a solution if you are able to solve the equation of motion. So there's a famous solution called the BPS solution, which is the Bogomolny-Prasad-Sommerfeld solution. And what they do is they say, let's take lambda to be 0. So you get rid of this, but you still require that phi, the magnitude of phi at infinity is eta. And then you can write the energy as the sum of squares as we did in the wall case. and then you have to solve first-order differential equations. And if you want another exercise, you can try writing the energy as a sum of squares. And then you use the ansatz that phi is some radial function times the radial vector, and W has this form. When you do this, then you can find solutions for these functions P of R and K of R, and they are some simple solutions. Okay? So the interesting story here is that Prasad and Sommerfeld found this solution just by guesswork, and then later on Bogomolny had this nice way of actually finding the solution systematically. So let's think about the symmetry breaking pattern. So to understand the properties of the solution, we first have to discuss exactly how to define, say, electromagnetism in this situation. So let's start with the symmetries. There's a global symmetry is where you rotate phi, the vector phi. So there's some rotation about some axis, about some angle, and this matrix R belongs to this group O3. Okay, so in general, you do this rotation, and the Lagrangian doesn't change. Okay, but there are some rotations that do even less. They don't change the field at all. Right? So if you transform phi by a rotation which is along the axis of phi times alpha, and you act on phi, then this doesn't do anything. Because if you have phi pointing in a certain direction and you do rotations like this, then phi remains the same. So there are some transformations, there are some rotations that are leaving the order parameter, which is the phi, unchanged. And this defines a subgroup of the full symmetry, and that is the unbroken subgroup. So this is actually rotations about one axis. This is an O2 subgroup of the full O3, and that is unbroken. So what is happening here is that when phi becomes non-zero, then the O3 breaks to O2. And an example would be you choose phi to be in the third direction, and you take this rotation to be in the first and second block like this. Then, of course, when you act R on phi, it does nothing to phi. Okay? So the symmetry breaking is O3 to O2. And now, so the point of all this is that we want to get to what is the photon in this theory. What is electromagnetism coming out from this symmetry breaking? So again, here's the Lagrangian. Now, if you look at d mu phi squared, it is d mu phi minus g, and then this cross term whole squared. And if you can open this out, and there'll be a term which will be this last piece squared. So there'll be g squared w cross phi whole squared. And so phi, so you can write this term as g squared eta squared w squared minus phi hat dot w squared. So this is like a mass term in the Lagrangian. Okay? So because this is like m squared times the field squared, and that's like a mass term. And so all the components of the gauge field are getting a mass when phi becomes non-zero, except for one component, which is the component along phi hat. So if w is along phi hat, then this becomes zero. So there are, in other words, there are two gauge fields over here which are massive, which get a mass, but one combination remains massless. And this massless gauge field is like the photon, so we call it the electromagnetic field. And so the electromagnetic field is the component of W along phi. And an example again, if you take phi to be in the third direction, then the electromagnetic gauge field is just the third component of W. So now that you know the gauge field, you might say, well, the field strength is just the curl of the gauge field. But this has certain problems because now if you assume this formula, then you get d mu phi hat dot W minus d nu phi hat dot W. And looks like there's a typo here. Okay, sorry. Okay. What did I do here? I'm trying to do a gauge transformation, but this is not completely correct. Okay. So ignore this line. But the point is that if you do a gauge transformation, then you would hope to get the same thing, but you don't. And the reason being that the d mu acts on the phi hat as well. And if your phi hat is changing in space, then you get derivatives of phi hat, and they spoil the gauge invariance of this. Oh, actually, maybe it's okay. What I'm doing is I'm saying if a nu goes to a nu plus d nu lambda, then this would become d mu phi hat dot W plus this term, right? So this is the gauge term, and yeah, and then you'd get extra derivatives of phi hat. Anyway, probably it's not written very well, but the point is that this is not a gauge invariant definition. So the other option is you say that my gauge field a mu is the projection of W in the direction of phi hat. So maybe the field strength should be the projection of the field strength in the direction of phi hat. But you see that this is now phi hat dot d mu, and then the gauge field strength has this quadratic piece as well. And so even if you choose the case where phi hat is just a constant, this is not equal to d mu a nu minus t nu a mu. So somehow the usual Maxwell B is equal to curl A is not holding in this case. So what you would like is a gauge invariant definition of the field strength, but one that reduces to Maxwell formula in the case where phi hat is a constant. And so one such definition was given by Tuft, which is he took a mu nu phi hat dot W and then added a piece d mu phi cross t nu phi with some coefficient, and which I couldn't find last night, so I left it as an exercise for you to find that coefficient. It's not hard to find because all that you do is you multiply this and you make sure that the quadratic piece, so like a W mu, W nu piece from here cancels the quadratic piece from here. Okay, so, but when you open this out, when you open out the covariant derivatives and you write things again, this turns out to be d mu a nu minus d nu a mu plus some coefficient times the derivative of phi, the ordinary derivative of phi cross the ordinary derivative of phi. So this is the formula for the field strength of electromagnetism in this theory. And as you can see that if you take phi to be constant, then these go away, these are 0, and it reduces to the usual B is equal to curl A formula. Okay, so now let's go back over here. So we have this formula, and now we want to know, well, if it's a magnetic monopole, then it should have a magnetic field, which looks like a Coulombic magnetic field. So now we apply this formula, with phi to be that expression given earlier, and the gauge field to be that expression given earlier. So let's first find the gauge field, A, which is phi dot W, but you see that phi is proportional to x hat, and W is orthogonal to x hat because of the epsilon symbol. So when you do this dot product, you'll get epsilon Aij, XA, XJ, and this will be 0. So the gauge field actually vanishes for this magnetic, for this configuration. However, if you look at this part, then your phi, this expression here can be written in full form like this. P is sine theta, cosine phi, sine theta, sine phi, cosine theta. This is the radial vector. And so if you take derivatives with respect to theta, you will get cosine theta, cosine theta. So this will be proportional to the unit vector in the theta direction. And then you can find the derivatives with respect to phi, and this will be the unit vector in the phi direction. So when you do E theta from here cross E phi from here, you will get something proportional to R hat, and it turns out to be this formula over here. So the magnetic field of this solution is going to be the monopole, the magnetic monopole magnetic field. Okay. So now let's try and do something more general. We've been focusing on O3 so far. Let's go to grand unification again. So in grand unification, you have some huge symmetry group, SU5, SO10, or whatever, and it breaks down to what we know today, which is SU3 cross U1. Yeah, so that's QCD times electromagnetism. Now, so we haven't discussed this in detail, but the vacuum manifold is isomorphic to this G by H. So just in terms of symmetry groups, you can find the vacuum manifold. And then there's a theorem which is derived using this isn't what they call an exact sequence in homotopy theory, which is that pi 2 of G by H is actually pi 1 of G by pi 1 of H if pi 2 G is trivial and pi 1 G is trivial. So this is a theorem in mathematics. And so the pi 2 of the vacuum manifold is going to be pi 1 of the unbroken groups. But the unbroken group is QCD and electromagnetism. And you know that U1 is a rotation in one dimension. So it is a circle. So pi 1, and you know that you can wrap around the circle. So pi 1 of H is actually Z. I'll discuss these discrete factors in a minute. But it means that whenever you take a grand unified theory, it necessarily has magnetic monopoles. You can't, just from the topology, because pi 2 of G by H is pi 1 of H, and that is Z, so then you're stuck with magnetic monopoles. So magnetic monopoles exist in all grand unified models. All right. So coming back to the discrete factors, remember I said H is SU3 cross U1, and pi 1 of H is Z. So what is this Z3 sitting over here? So basically, there are elements of SU3 which are some phase factor e to the I 2 pi by 3, e to the I 4 pi by 3 times the identity. But those kind of elements are also in U1. So if you didn't have this discrete factor, then you would be double counting those transformations. So the center of SU3 is also contained in U1. So kind of pictorially, this is a caricature. The U1 is a circle, and SU3 is some complicated group, but there are some common points in them. And so a monopole corresponds to pi 1 of H. So for example, you could have a wrapping all the way around, but it turns out that a shorter path is the one that goes down here and then comes back through the SU3. And so the fundamental monopole in this is actually has SU3 charge and U1 charge. So it's both, it has both kinds of charges, and that is the fundamental monopole. So in sort of dealing with magnetic monopoles, it's important to keep track of these discrete factors. So now let's come to cosmology. So the formation of magnetic monopoles is exactly as we described earlier, that you have to assign this phi vector, or whatever the order parameter is, to different parts of space. And just by chance, you will get places where the order parameter looks like a hedgehog. And if you have a hedgehog configuration, then you're forced to have a magnetic monopole somewhere. So, so the magnetic monopoles are formed due to this random distribution of the order parameter. And magnetic monopoles are heavy. And maybe I should have given the mass somewhere. Maybe you can see it from here. This is 1 over the coupling constant. So if you find just the magnetic energy, it'll go like 1 over coupling constant squared. So you can see the coupling constant is in the denominator, and coupling constants are taken to be small. So the magnetic monopole will be heavy. And so it'll be non-relativistic, and it will redshift like matter. So the energy density in magnetic monopoles is redshifting like 1 over a cubed, where a is the scale factor. But these monopoles are forming in the radiation epoch, because it may be at the grand unified epoch. So their density is falling off as 1 by a cubed. The energy density in radiation is falling off as 1 over a to the 4. So the magnetic monopoles quickly overwhelm the cosmic energy density. So omega and m, defined to be rho m by rho gamma, the radiation, turns out to be 10 to the 29 times the initial omega in monopoles. And the initial omega in monopoles you can estimate sort of in a very crude way. You can say there's 1 monopole in every horizon. And even then, this turns out to be a huge omega m. And so these magnetic monopoles are severely constrained. And so this was called the magnetic monopole overabundance problem. And as you might know, this led to the idea that maybe there's inflation after you form these monopoles, and then the inflation gets rid of them. But there are several other constraints as well. So there's overclosure. So this being less than 1 or something would be a constraint. But there are also other constraints like the Parker bound, and I'll discuss that in a minute. And as I said, inflation, if it occurs late enough, can dilute the monopole energy density. So the Parker bound works like this. So if you have a magnetic field, then you have magnetic monopoles in that magnetic field, and the monopoles start getting accelerated because of the pull of the magnetic field, and so they eat up the magnetic field. Okay? So if you observe magnetic fields, then you can say, well, that must put a constraint on how many magnetic monopoles I have. And, oops, sorry. So the survival of the galactic or cosmological magnetic fields places upper bounds on the flux of magnetic monopoles. So this is you can do a simple estimate as follows. The energy gain rate by the monopoles is just the force times the velocity. So QM being the magnetic charge times the magnetic field times the velocity tells you the rate at which a monopole gains energy by being in a magnetic field. And so there's a certain time scale on which the magnetic monopole will eat up all the energy of the magnetic field. And so that is denoted by tau. And since we observe magnetic fields in galaxies, that time scale should be longer than the age of the universe because these galaxies have basically survived Hubble time. So T0 has to be less than tau, and then tau is basically the energy density in the magnetic field, which is B squared, divided by the number density of monopoles and the rate at which the monopoles are eating the energy. And so this turns out to be B, QM, NMV. And this B we can take to be the galactic field, which is 10 to the minus 6 Gauss, or in particle physics units, 10 to the minus 26 GeV squared. Then if you define the flux to be the number density of monopoles times the velocity, then that has to be, so you can take this on this side, bring the T0 down here, and work out some numbers, and that will be, the flux has to be less than, well, or, so if you take them to be relativistic, then this would just be the number density, and that has to be less than 1 by 10 to the 4 kilometer cube. So it's about 1 monopole per Earth volume is your constraint. This has been refined and discussed a little bit more. You can, but basically there are strong constraints on the flux of monopoles, and this is called the Parker bound. Okay. The other interesting situation is the electroweak model, and in the so you might ask, are there magnetic monopoles in the electroweak model, the standard model of particle physics? So let us look at that a little more closely. The standard electroweak model has an SU2 and a U1, and it breaks into electromagnetism. So this is the left-handed SU2, and this is the hypercharge, U1. In this case, the order parameter is the Higgs field, and the Higgs field is a doublet of, so there are two complex numbers, two complex fields. So I've written them in terms of real fields. Phi1 is real, Phi2 is real, Phi3, Phi4 are real. And the potential is the same kind of potential, phi squared minus eta squared whole squared. So the vacuum manifold is basically Phi1 squared plus Phi2 squared plus Phi3 squared plus Phi4 squared is eta squared. And so the vacuum manifold, so this is the equation for a 3-sphere. Okay. Right, so it's in one higher dimension. So it's a 3-dimensional sphere. So yeah. And there's a way to actually write the 3-dimensional sphere in terms of angles, and that's called the Hopf parametrization. And so phi is cosine alpha e to the I beta, sine alpha e to the I gamma. And so alpha, beta, gamma you can think of as angular coordinates on a 3-sphere. Okay, so again, let's think about how do we define magnetic fields in this U1 EM? So just as in the O3 case, you can't write A mu nu is d mu A nu minus d nu A mu. Instead, what you have to do is to take, you have to have an extra term over here, which is d mu phi dagger d nu phi minus the d nu phi dagger d mu phi. And if you think of this, and then you expand this out, you expand the covariant derivatives, what you find is that A mu nu is the curl part minus the gradient of phi dagger, gradient of phi, and so on. So in other words, the magnetic field is defined as curl A minus the gradient of phi dagger cross the gradient of phi. Okay? So this is the logic for this is exactly as the logic we had in the case of the O3 model, that we had to add this extra piece to maintain gauge invariance and to reduce to Maxwell in the limit that phi is uniform. So, but now you can take phi to be, for example, cosine theta by 2, sine theta by 2, e to the I phi. And when you do this, then you find that B goes like r hat by r squared. And so this is clearly the field of a magnetic monopole. So this would imply that the standard model also has magnetic monopoles. Sorry? The magnitude would be, no, the eta squared would cancel, and it would be something like 1 over g. There would be a g over here. So let me go back over here for just a minute. So remember, we said when we were discussing topology that magnetic monopoles form when there's a mapping from S2 to something like an S2, right? So there has to be a manifold which has a hole in it. But the vacuum manifold here is an S3. So if you want to draw an S3, then you have to draw a solid S2 and identify certain the points. But the point is that there are no holes of that kind in S3. And so it's a little confusing why the vacuum manifold seems trivial as far as pi 2 goes, and yet you have configurations that look like magnetic monopoles. So, okay, there are many ways to think about this, and this is where sort of gauge fields start coming into the picture. That although this looks like an S3, when you think of the whole model, then it's more, it's better to think of it as an S2 cross S1 because of the gauge fields, the particular way of the gauge fields are set up in this. And this has actually been known that the S3 is isomorphic to S2 cross S1 locally because it's called the Hopf vibration. In any case, we don't. What I'm saying is that life can be more subtle than just looking at the vacuum manifold. So the other thing you notice here is that there's an e to the I phi here, and there's sine theta by 2. So when theta is pi, so at the south pole, there is this field is multivalued here. And so, in fact, what happens is that you have a magnetic monopole, but there's a string attached to it. And so this was first discussed by Nambu, and he called them electroweak dumbbells. So basically, you have a magnetic monopole where divergence B is not zero, so it is a true electromagnetic monopole. But then on the south pole, there's a string coming out which eventually goes to an anti-monopole. And this string, you might say, well, this is, so you shouldn't think of the string as sort of returning the magnetic flux, because the string is made up of a completely different field, the Z gauge field. So this is a configuration of an electroweak monopole and an electroweak anti-monopole connected by a Z string. This is kind of very similar to, you have a quark-antiquark pair, and there's a string, a QCD string in between. So the quarks carry electric charge, right? So you have electric charge plus 1/3 and minus 1/3, and there's a string in between, but the string has nothing to do with electric fields. It's some QCD string. So the same thing here, you have magnetic fields, but the string is made up of some other field. So anyway, so these dumbbells can exist in electroweak physics.
The string length is, the string width is the mass, but the length is the...
So this is an interesting, so this brings me back to that earlier cautionary remark that I made. Let's see. that you have a non-trivial topology does not imply a static solution of the equations of motion. So in fact, over here, there is no sharp, well, let's say. So if you take, so this can't be a solution because the string is pulling these together. But in principle, you can remove these to infinity, and you can just think about the string solution, and the width of that string solution will be the mass of the Z inverse. But it won't be stable. So although the sort of topological argument tells you that the Higgs can't be in its vacuum manifold along these points, it doesn't tell you that there's a stable or a solution or a stable solution. So, but there is a way to discuss the existence of these monopoles and the strings in a topological way by considering the Hopf vibration. And using that, we've simulated the distribution of these strings based on random distributions of the Higgs parameter, and we get a tangle such as this. The blue dots are, say, monopoles, the red dots are anti-monopoles, and then there are strings connecting them. But you might say, well, what's good is this? Because the strings will bring the monopoles, anti-monopoles together, they'll annihilate, everything will go away. So what's the point of this? The point is that where there are magnetic monopoles, there are magnetic fields. So even if all the monopoles go away, you will be left with some magnetic field. And it is of interest to calculate what that magnetic field is and what it means for the magnetic field today in cosmology. So now I'll come to back to the grand unified case and sort of connect a little bit with the first lecture. So, so the SU5 transition, the SU5 grand unified model is where SU5 breaks to 3, 2, 1, and then there are discrete factors, and then the SU2 cross U1 breaks to SU3 cross U1 electromagnetism. The Lagrangian or the bosonic part is just what we've written earlier, and the potential can have many terms. It can be a trace phi squared, trace phi squared squared, trace phi to the 4, trace phi cubed, and so on. And again, let me consider the case where gamma is small, so we can actually ignore this term for the moment. Then if the cubic term is small, then the initial symmetry is SU5 cross Z2, because there's the additional symmetry of phi going to minus phi. And then in the first stage, the Z2 also breaks, and then of course you have domain walls. So there are magnetic monopoles in this transition because there's a U1, right? And so the pi 1 of the U1 is non-trivial. And you have domain walls. So in this particular case where gamma is small, there are monopoles and domain walls after the first symmetry breaking. If gamma is small, then the domain walls are biased. Okay? So this grand unified theory has structures that resemble domain walls, and it has magnetic monopoles. So then the question arises in cosmology that if you have this transition, then you'll be forming both magnetic monopoles and domain walls. And the monopoles will be hitting the domain walls because the domain walls are moving, the monopoles are moving. And then the question is, what happens? One option is that the monopole just goes through the domain wall. And the other option is that somehow the monopole and the domain wall interact and something funny happens. And so we've looked at this, and the outcome, this one or this one, depends on how the walls and the monopoles are oriented in the field space. So I'll explain this in a little more detail. Remember, back from lecture 1, the domain wall would be, if I went from 2 to 2 minus 3 to minus the same thing. So this is the topology, the minus. But there are other options. There are 2, 2, 2, minus 3, minus 3. And then on this side, I switch one of the 2's and the minus 3's. And then in this last case, I am switching both minus 3's with these 2's. So the 2, 2 have come at the end. So all of these have the same topology, and all of these are domain walls. And yeah, so, and if you remember, this one is the lightest domain wall, whereas this is the most numerous domain wall. Okay, so we will consider the lightest domain wall. Now it turns out that the monopoles you can take. So of course monopoles. So let's see. The monopoles reside in a 2 minus 3 block. So it can be this 2 and this minus 3, or this 2 and this minus 3. There are many ways that you can put a magnetic monopole solution in this model. So the monopoles reside in a 2 minus 3 block. That's where all the winding of the monopole is. And so what I will do is I will look at a monopole and wall, and the wall I am taking to be in this lightest configuration, where the 2 2's are switched with the 2 minus 3's. So there are 6 ways I can embed the magnetic monopole on the left, right? I can take this 2 and this minus 3, or this 2 and this minus 3, 3 choices for 2 and 2 choices for minus 3. So there are 6 embeddings for monopole on left and 6 on right. But if I'm looking at the monopole domain wall collisions, then there are only 2 distinct cases. I can take a monopole in the 3, 4 block. So I can take this 2 and minus 3. I can put the monopole here. And then this will go into minus 3, 2 on the right, this one. If I take monopole in the 1, 5 block, then I have 2 minus 3 over here. And that will go to a 2, 2 on the right. Okay? So either, so remember there's a, domain wall, and there's a magnetic monopole, right? And this has to try and go over here. Right? But this occupies a certain part of field space. And in this case, right? So on this side, it's occupying 2 minus 3, and then it might go into, again, minus 3, 2 on the right. But the monopole in the 2 minus 3 block would have to go into a minus 2, 2 block. So in a sense, it can't go there because it needs to be in a 2 minus 3 block. Yeah? So the monopole has to live in the 2 minus 3. So we've done some simulations. So if you start with 2 minus 3, and then the question is, if we take a wall, okay, so it's kind of complicated. So if we put the monopole here in this block, then the question is what happens? And then here we're plotting the potential energy, and then here we're plotting the magnetic energy. So you can see initially the wall has no magnetic energy, and then all the magnetic energy is in the monopole. So this is a slice. And the potential energy, the magnetic monopole has some potential energy, and the wall has some potential energy. So this is the initial state. And then basically nothing happens. The wall comes through, and it just goes through, and the magnetic monopole keeps sitting where it was. This is a simulation we did, I think now, many years ago. So this is the case. This is the case when the monopole winding is in this sector. So now you consider the case where the monopole winding is basically in the 1, 5 sector, 2 minus 3, and then it has to go to a 2, 2. And then you can see that the monopole gets destroyed. Again, this wall comes, and then here there's some interaction, and the wall goes through, but there's nothing left over here. And then the magnetic energy, the magnetic monopole is here, and then it starts spreading onto the wall, and there are some ripples on the wall. So this led to the idea that maybe in this kind of system, where you have monopoles and walls, and the walls can sweep away the magnetic monopoles, and in that way solve the monopole overabundance problem. And then, so the first objection to this is that if you have walls that interact with magnetic monopoles, sweep them away, then you're stuck with a magnetic monopole, then you're stuck with a domain wall problem. The domain walls are also not good for cosmology. But you can have a small bias, and then if there's a domain wall, then there's a pressure that acts on one side, and the tension, which is due to the curvature, is acting on this side. And so in the beginning, the pressure, this gamma is very small. So the pressure is small, and the walls move as if there was no bias at all. But eventually, the walls get more straight because of the Hubble expansion, and R starts becoming large, in which case the tension is small. So then when the tension drops below the pressure, then the pressure drives all the walls to one side, and the pressure wins, and the wall network can annihilate. So the assumption is that when the walls annihilate, it will also imply the monopoles that sort of got stuck to the wall and started spreading on the wall, that all that will also annihilate. But this hasn't been tested, and so I think it requires more work. But in principle, this would be a natural solution to the monopole overabundance problem. People have also been looking at these interactions. One idea is that monopoles are coulombic on one side, so their magnetic field is 1 over r squared. But it can happen that on the other side of the wall, the monopoles are confined, and that can also happen. And then there was some papers on monopole wall interaction that can lead to gravitational wave signatures. So I'll just give you the links, and you can try them out. There's some nice videos. Okay, so I will summarize. So magnetic monopoles are predicted in all grand unified models, yet the abundance of heavy monopoles in the universe is highly constrained. Inflation has been proposed as a solution, but I feel it is disconnected from the particle physics model. So another solution involving defect interactions may also work, which is what we just discussed, that you have biased domain walls may be able to sweep away monopoles. And the scenario needs further study, as well as the production of gravitational waves during defect interactions. Then you have electroweak magnetic monopoles that can produce primordial magnetic fields, and these are being currently probed by observations, namely the electromagnetic cascade from TeV blazars. So this is an exciting area as well. And the last point is that if magnetic monopoles exist in the fundamental theory, but have been erased in the universe, then it should be possible, in principle, to create them in the lab. And this problem has not received as much attention, well, kind of, but not in so much detail. Okay, I realize I've finished a little early. So let me take a few questions, and then I have something else for you. Any questions? Yes?
Hello, yeah. So the definition of mu nu that you have given in both cases, is that like unique or canonical? Does there exist other gauge invariant definitions of mu nu that will give the same magnetic field sort of?
So what you're trying to do is to cancel off the quadratic piece in the W mu nu, and you have to do it in a gauge invariant way. This is the only way I know.
And one more thing regarding the Parker bound that you showed, I think. Yeah. So there you mentioned that the rate of energy gain was QMBV. This sort of is a bit naive question, but seems like the monopoles are in a magnetic field. So what would that V correspond to?
So the V would be the velocity of the monopole.
No, like it's in a magnetic
Oh,
field, so it should be accelerating, right?
yeah, so ideally you should calculate it. Yeah, you should do a more careful job. Here it was just V is some order 1 factor. In fact, here in this language, I have kept V as V. So this is called the flux of the monopoles. So it's really a constraint on the flux and not on the number density. Yeah.
And if the monopoles are moving and if the velocities are high enough, can the electric field energy can give a significant contribution to these bounds?
So moving magnetic charge produces electric field.
Yeah.
So there's a plasma as well. And so the plasma tends to short circuit electric fields. But it's a good question if there is some observational effect. At electroweak, it's a 10 to the 2 GeV.
So then inflation has nothing to do with engineering.
Well,
Overabundance of those.
well, they would get eliminated just from their dynamics because the string will pull them together, the monopole, anti-monopole will annihilate.
So this electron is always in a string.
Yeah, yeah.
I'm interested in your simulation for the Z string and monopoles.
Sorry, which simulation?
The Z string. Yeah, you had simulation in 2022, 3 years ago. Yeah, I'm interested in this. So, this, as you said, Z string is unstable, so it will quickly disappear.
Right.
Maybe in the W direction. Is it
so this
correct?
was a purely topological simulation. So there was no dynamics in this. The point of this was that that you can use the Hopf vibration, the topology coming from the Hopf vibration, to actually find where the zeros of the Higgs will be. But this will rapidly go away. You're actually completely correct on that.
I see. Another question is, okay, you mentioned strings and monopoles and domain walls, and is there any possibility of having texture in the other universe?
Textures?
Yeah, I'm wondering about this for some time.
So in the electroweak model, people have discussed textures because it's a 3-sphere, and the texture is pi3 of the vacuum manifold being non-trivial. But these are gauged textures, and I think they're related to barrier number violation also. I'm not sure about that. But people have discussed it. I can give you references.
Okay, yes, thank you very much.
The original monopole idea, there was a Dirac string. But these are real.
These are real strings, yeah. But made of something else. Yeah. Okay, since looks like there are no more questions, so I thought I would ask you some questions. I thought, since I have some time, I thought I'd give you a quiz. Okay, so you have to say true or false, okay? Domain walls can be used to build a house. False, okay. So now we get serious. Bogomolny method evaluates the energy of a domain wall without solving any differential equations. True or false? So you're saying true or false? True. Is that everyone agrees with that? So you can find the energy of this whole configuration without actually solving any differential. Yeah, that's trivial. Okay, okay. Biased walls live forever? False. Okay, easy. Biased walls do not lead to a gravitational wave background. False. Okay, so they move and they give dome. A collapsing spherical domain wall emits gravitational waves. Sorry? False. Okay, no quadrupole moment. Okay? A collapsing spherical domain wall emits gravitons. That means you include some quantum effects. Anyone? True? 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 False? True? Well, it's true because just like gravitational collapse gives you Hawking radiation. So this is a time-dependent background, so it should give you some radiation. Non-self-intersecting cosmic string loops mostly look rectangular. True. Okay, you saw that animation. Oh, sorry, I screwed up over here. Just a minute. Non-self-intersecting cosmic string loops. So meaning the loops that don't self-intersect, whether they look rectangular. Okay. Cosmic strings only produce a stochastic background of gravitational waves and no other signature. True or false? False, okay. They have also bursts and things. Yeah. All right, should we go on or getting tired? I think you're doing very well, by the way. The Nambu-Goto description of a string is valid under all circumstances. False, okay. Cosmic strings can be infinite. True, okay. Some strings can carry electric currents. True, okay. Superconducting strings.
So cosmic strings can be infinite.
Sorry?
So cosmic strings can be infinite.
Yes, yes.
There must be a horizon when they are formed.
They go all the way. They don't never close on themselves. They just keep going.
All the way, but there is a finite horizon at any particular time. Causality can do that. Nothing can be bigger than the horizon at that particular
No, it's kind. It's
1 by h is the causal horizon.
it's kind. It's
Photons can propagate at any given.
you would think, but since all horizons are sort of going through this phase transition at the same time, that's the FRW model. So then your strings just percolate. Strings can't have ends because of the topology. So either they are closed or they just keep on going. So, okay, well, all right, so we can discuss that more for some strings. A magnetic monopole is the same as a hedgehog, the animal. Okay. Different types of topological defects don't interact. Magnetic monopoles can only carry abelian magnetic charge. Abelian means maximum. Good. Div B equal to 0 in electroweak standard model. B is the magnetic field. False, okay. Experimentalists are looking for magnetic monopoles at CERN. Sorry? Yeah, the model experiment. Very good. There can be a universe inside a monopole. True. Yeah. Okay, very good. 100%. Thank you. So remember I discussed the topological inflation. where since if you have one of these defects, there is some region of space which has phi equal to 0, and where there's lots of energy. So that starts inflating. Okay.
So we go for coffee break early then today.
Time, Tanmay,